Welcome to Lab M12, Simple Harmonic Motion and Resonance. The objectives of this lab are to study the properties of simple harmonic motion, to demonstrate Hooke's law, and to study the relationship between kinetic and potential energy in simple harmonic motion. You'll be using a 2-meter long aluminum air track, gliders, a speaker, an amplifier, adjustable air supply, spring set and weights, knife edge to measure spring constant, a photogate, and a motion sensor. The air track has holes through which the air gushes out and lifts the gliders such that they move almost without friction on the air track. For part 1, begin by setting up the springs appropriately. Don't stretch them beyond their elastic limit and don't let them sag and drag on the track. Locate the photogate so the glider cuts off the beam when the glider is in the equilibrium position. You have to show experimentally that the period is independent of the amplitude. For the next part, add weight to the glider and again study the period versus the total oscillating mass. The restoring force on the glider is 2k delta x. For the third part, measure k directly by hanging spring vertically on a knife edge assembly. Record the stretch produced by a series of weights, but do not exceed the elastic limit of the spring. Graph f versus delta x for each spring and obtain a best fit straight line. The slope will give you the spring constant. For the fourth part, replace the timing plate with aluminum vane. Set up the motion sensor approximately 60 centimeters from the vane. Connect it to the interface and create an experiment in Data Studio. Make sure that the motion sensor is properly aligned so that it senses only the vane and not the card. Practice a few times and generate smooth varying position versus time plots using Data Studio. Then study the behavior of these graphs and check with your predictions. For the next part, detach the fixed spring and stop and place the speaker as shown with the spring looped through the small slot. Connect the amplifier using DIN 9 pin to the A channel of the interface. Then connect the speaker to the amplifier. In Data Studio, select channel A and set Power Amplifier as your instrument type. This will open up the Signal Generator menu, which you will use to set up the voltage and frequency of the signal. The voltage determines the amplitude given by the speaker and the frequency sets its frequency of oscillation. To get good results, begin with setting up the frequency to the natural frequency of the system. The speaker then moves with spring according to the voltage and frequency that you have just set. After that, start the signal and you'll observe that the glider starts moving and slowly gains velocity and amplitude. You can then observe that both the maximum velocity and the amplitude settle down to a constant value after some time. Then you can easily read off the amplitude values from the position versus time plot and note down the corresponding frequency. Try different values of frequency until you get the maximum value of amplitude. The sketch of amplitude squared versus driver frequency should look like this. From the values of amplitude and frequency that you just noted down, you can create a plot and this plot should look approximately like the curve we just saw. With more number of data points, you can get an even better fit for the plot.